So it's my great pleasure to introduce Georgia Benkart from University of Wisconsin-Madison, and she will tell us about Markov chains from Weyl modules for UQ-sl2. Thank you, Georgia.
So thank you all very much, and I'm very happy to be here. Not here, but okay. So I want to talk about something that goes back a long way to the Mackay correspondence back in 1980, so over 40 years ago. And this is when computers went from being clunky big machines, to being things that sat on everybody's desktop. And John Mackay was just experimenting with his computer. And he looked at finite subgroups of SU2, so 2 by 2 unitary matrices of determinant 1. And he took the simple modules of G. And he took the natural representation. So you have 2 by 2 matrices, you're multiplying C2. And he took the tensor product with V. And he looked at these multiplicities and formed from them a quiver. So the quiver has nodes corresponding to the simple modules. And the number of arrows from I to J is just this multiplicity. And the big miracle was it turned out to be an affine Dinkin diagram of type ADE. So this was, really kind of groundbreaking. Everybody started finding the Mackay correspondence under every rock and behind every door. And really, why should there be this connection between these two objects? So let's form a matrix with these numbers, these multiplicities. Call it the Mackay matrix. And what's really going on is that this 2 times the identity is an affine Cartan matrix of type ADE. The mark on the node of the diagram, the Dinkin diagram, is the dimension of the simple modules, the SJs. And if you take those dimensions and put them in a column, you actually get an eigenvector for the Mackay matrix, and the eigenvalue is 2. So if you were to take this matrix C, this affine Cartan matrix, this S would just be the null vector. So something you might know from studying affine Kac-Moody algebras. So here's the picture. So there are 2 infinite families of subgroups. They're the cyclic groups of any order n. They correspond to type A affine Dinkin diagrams. They're the binary dihedral groups. They correspond to the type D. And then they're the binary tetrahedral, octahedral, and icosahedral, and they correspond to type E. So the blue node here is the affine node that corresponds to the trivial module for the group. The pink node is the thing that we're tensoring with. So the question you could ask is, are there Mackay matrices in other worlds? And a good other world to look at is the world of finite dimensional Hopf algebras, because we have a tensor product. So I'm going to take a finite dimensional Hopf algebra over an algebraically closed field of characteristic 0. I'm going to take a finite dimensional Hopf module with character. It's just a trace. So when I say character, I mean trace. Take the simple modules. Okay, so here's the first problem. the tensor product may not be completely reducible. So we can get around that if we assume H is semi-simple, but then we're sort of really limiting things. So I don't want to assume that. But what I want to do is look at the multiplicity of Sj as a composition factor in this tensor product. So I'll let that be Mij. Another way to phrase this is that in the Grothendieck ring, if you multiply these two isomorphism classes, you'll exactly get these numbers. So in this setting, it looks like the previous case. So this is what I'm going to call the Mackay matrix. And with Carly Clevens and Vic Reiner, a couple of years ago, we actually looked at something called chip firing on Mackay quivers in Dinkin diagrams. So the idea here was you put a bunch of chips at each node and you fire, and this Mij tells you how many chips should go from node I to node J. And these Mackay quivers and Dinkin diagrams have actually beautiful properties with respect to chip firing. They get to a stable configuration and all sorts of things. So Vic Reiner continued this idea with Grinberg and Huang and showed that if you take the vector of dimensions of simple modules, that you always get an eigenvector, and the eigenvector has eigenvalue to the dimension of V, i.e. the trace of the identity. Also, if you take the dimensions of the projective covers of the SI, or these are the projective and decomposable modules, they, if you put their dimensions into a vector, you actually get a left eigenvector. So there's actually a whole story going on with the projectives. I'm not going to talk about it today, okay, but it's a very interesting story. So let's think about Mackay matrices for Hopf algebras. This is joint work with Reka Biswal, Ellen Kirkman, Van Neugen, and Jiru Zhu. Just appeared in Canadian Journal of Math. And okay, so we have a finite dimensional Hopf algebra. We have the coproduct. I'm going to apply X to SI tensor V. So what happens when I apply X to SIV? Well, the first factor of the coproduct hits on the first factor, and the second factor acts on V. So here I'm just using kind of standard Hopf algebra notation. I wrote the sum sub X, meaning that these factors in the tensor product depend on X. That's the only thing it means. So when I take the trace, I get the trace on SI of the first factor and the trace of V on the second factor. That's the trace on the tensor product of X. And because I had written SI tensor V as the sum of the SJs, I get this equation. Now I'm going to write this equation a little bit differently. So I'm going to form a vector with the traces of X. So I take an element X and I just evaluate the traces, the characters. This is actually a column vector. And what you can show is that this is actually sort of an eigenvector for the Mackay matrix. When you multiply this Mackay matrix times this vector, you get a sum of similar vectors. So where this is coming from is this first term over here is actually the right term over here. And the term over here is this term just rearranged. So this is a matrix equation. This is the ith component of it, the ith row. Now, what happens if G is group-like? Well, it becomes extremely simple. It's just that this vector at a group-like is just an honest eigenvector of M. So now I'm going to talk about Markov chains. This is joint with Percy Diaconis, Martin Liebig, and Pham Thiep. Appeared in Journal of Algebra a little while ago, about a year ago. So like Sue Sierra, we were all at MSRI. We had offices all in a row, and we just bounced back and forth like a Markov chain talking to each other. So this is where this story takes place. And of course, you recognize probably Percy Diaconis. And this is why it suddenly went from algebra to probability. So take any finite group, take the irreducible complex characters, take a faithful complex character, and take the product. So multiplying characters is the same as taking tensor products. So this is really just taking the tensor product of the two representations for which these are the characters. And what we're going to do is we're going to pick xj, a chi-j rather, from the right-hand side with probability proportional to its multiplicity, the mij, and its dimension. Okay. So here's the chance of moving from chi-j, chi-i to chi-j by multiplying by zeta. And that's it. So it's the multiplicity times where you end up, the dimension of the module where you end up over the dimensions of the things you start with. That's the chance of moving from chi-i to chi-j by multiplying by zeta. So this tells me that the Markov chain and the Mackay matrix are related by a very simple matrix formula. So here, the MD is this top part. When I look at it, coordinate-wise, the D inverse is giving me the term down below because I have a diagonal matrix with chi's on the diagonal, and when I take its inverse, they become inverses. And then the zeta 1 is just a scaling factor. So it's sort of, you know, all of a sudden we're doing probability, or we didn't realize we were doing probability. We were just doing algebra, and it became probability. Okay. So this is the relation that we had on the previous page. Okay, but we can say more. So if you take an eigenvector of M with eigenvalue lambda, then you get an eigenvector for K with eigenvalue 1 over zeta of 1 lambda. So that's easy, just put it in up here and you just check it works. And if you take a left eigenvector of M with eigenvalue lambda, then WD is a left eigenvector of K with eigenvalue 1 over zeta of 1, the dimension of zeta, the function, the module corresponding to zeta times lambda. So everything is connected. If I'm doing probability, I want to know eigenvectors and eigenvalues. And they're just related to this Mackay matrix. So here's an example. Just take the group sl2, 2x2 matrices of determinant 1, over a field of characteristic P bigger than or equal to 2. What are the simple modules? Well, the simple modules look like the simple modules for sl2, the Lie algebra, or the Lie group, but they stop. There are only P of them. And the dimension is A of the VA is A plus 1. So this module, this last one, is really interesting. It's both simple and projective. And I'm sure people realize this, sort of recognize that this is the Steinberg module. And it has all sorts of fabulous properties. So here's what's going on. Here are these Ks. So when we tensor, we go from either A to A plus 1 or A to A minus 1. And so these are the probabilities. If you're Percy Diaconus, you say, oh, those are the probabilities. If you're Georgia Benkart, you say, oh, I'll go back to the Mackay matrix and I'll compute them. And that should be what the Ks are. Okay. So these are the Ks. This is the probability of going from A to A plus 1, going from A to A minus 1, and so forth. So this is the Mackay quiver. And you notice something here. So this is the trivial module, the blue one. The pink one is what we're tensoring with, V1. It's a two-dimensional module. And everything, you just go left, right, till you get to the end. And you get a projective module. And when you tensor it, you get a projective. And it has two copies of the one labeled by P minus 2 and two copies of the one labeled by 1. So that's why we have double arrows. And that's the quiver. So what about SL2P squared? Okay, so over a field of P squared elements, this is the quiver. Okay, so it sort of looks like the quiver that we had across a line, but then there are these jumps to the line below, So this is the tensor walk. If you hit the right-hand boundary, you bounce to the left, but you also bounce down with various multiplicities. Okay. So we were inspired by certain things that dealt with probability Markov chains. The first one was by looking at this Imard-Voronoi tensor walk on SU2 representation. So what is SU2? What do the representations look like, the simples? Well, they're just infinitely many, and they're all in a line. And what happens when you tensor with when you tensor with the two-dimensional representation, you either go left, right, left, right, left, right. So this walk had been studied before. Also, there's something called the gambler's ruin for SL2P, studied by Pittman, or the mathematician's ruin, if you get involved with it. There's also a 2008 paper by Jason Fullman on complex tensor Markov chains. So these are the three things that really motivated us and inspired us to look at these Markov chains. So take a finite group, take an algebraically closed field of characteristic P, look at the irreducible Brouwer characters. So Brouwer characters are just a certain kind of character that play a very important role in modular group theory. Take the P prime conjugacy class representatives. So the order of the elements in these classes are relatively prime to P. And then we can say what the eigenvalues are. They're just ratios of the things you're tensoring with over evaluated at this conjugacy class. And these are the eigenfunctions. So these are functions that depend on chi. So when you put in chi, you get either a left eigenfunction or a right eigenfunction. So here's an application. If you take a finite group over a field of characteristic P, and you consider the Mackay quiver, you have the vertices corresponding to the simples. You have the tensor Markov chain. So I'm tensoring with V. I'm going to assign a stationary distribution to the nodes. What is that? That's just the probability you put on each node to begin with. Where did that come from? It came from the Wedderburn theory when you don't have a semi-simple algebra. So your group algebra decomposes into projectivine decomposables, and the multiplicities are these dimensions of the SI. Okay. So if I had a semi-simple algebra, I just have the dimension of SI squared, Sj squared over the group. And that would be just dividing things up according to the Wedderburn decomposition of the group algebra. So then K of E, the transition matrix, is just going to be this chi-ij, kij, which is the dimension of D inverse MVD. That's the transition matrix of the corresponding Markov chain. It's a chance of moving from SI to Sj with tensoring with V. Okay, so what did we discover? We discovered that the rate of convergence to stationarity is challenging to compute. So if you were trying to figure out how many times do I have to take a tensor product to get close to where I began with, that's hard to compute. And similar considerations with the small quantum group or restricted quantum group give a new feature. And this new feature is Jordan blocks of size 1. So this is like in the previous talk where you get generalized eigenspaces. This is what we're getting with here. And so Percy said in every Markov chain that he had dealt with before, he never had to deal with generalized eigenspace. So this is sort of a good example of where you can find them and find them in abundance. So here's what happens in looking at the finite quantum group. The simples are, if we have a primitive nth root of unity, n odd, n greater than or equal to 3, they're numbered from 0 to n minus 1. These are the projective covers. Chari and Premet discovered what the projective covers are. So everything below the top one is the maximum submodule. And then the maximum submodule has a submodule that's isomorphic to the top thing. So if you take V equal the first one, the two-dimensional one, then this is the rule. Add one, subtract one, but don't do it if you run off an edge. When you get to the last one, you get a projective, and the projective has these components. So this is the chi matrix. These are the characteristic roots of it. They're nice. This is the quiver. So we went from a straight line sort of in the group case to this circular thing, the root of unity case, you can see that the n-1, when you tensor it, you get 2 copies of 0 and 2 copies of n-2. So I'm going to talk just at the end here about the Mackay quiver for UQSL2. It comes from looking at the semi-simple tensor category. QRED, this is joint work with Samuel Lopez. It uses the fusion product and the truncated Clebsch-Gordon formula for the finite quantum group. So here Q is a primitive 2L3 unity. These are the simples. There are only L-1 of them. Our inspiration came from a paper of Iohori, Lara, and Zhang in 2019. They used a similar fusion product for tilting modules. And these are the tensor rules. And this is the quiver. So again, you go from something that's circular to something that is a straight line. This is the Mackay quiver diagram of type AL-1. So again, these are the numbered 0 to on the left to L-2 on the right. And the thing we're tensoring with is delta 1, the 2-dimensional one, which is the pink one. So when you look at the Cartan matrix and you look at the eigenvectors of M, the Mackay matrix, you get Chebyshev polynomials of the second kind. These are polynomials that satisfy the U0 is 1, U1 is T, and then this recursion. And you notice if you move this term, the R-1 term, to the left, it's saying that if you take T times UR, you get +1, -1. So anytime you have a +1, -1 type tensor product, you're going to get Chebyshev polynomials of the second kind. And these are the eigenvalues. They're nice. Just powers of Q, Q inverse. The M's are the exponents of the root system of the Lincoln diagram. L is the Coxeter number. And for any Cartan matrix, finite Cartan matrix, you have similar eigenvalues and similar eigenvectors. This is in a paper of Eddinghoff and Kovanoff, 95. So when we take tensor powers, Iohori, Lara, and Zhang showed that this is a Jones algebra. It's a certain quotient of the Temperley-Lieb algebra. That's a famous Dinkin diagram or diagram algebra. What we showed was we also get a Jones algebra. Tensor powers decompose, and these numbers, multiplicity numbers, CA, have interesting expressions in terms of Fibonacci numbers. Also, they have interesting connections with number sequences in all the cases. These are the tensor product rules. So add 1 if you can, subtract 1 if you can, and don't if you don't. This is the Mackay matrix. And these are the powers of the Mackay matrix. So the powers of the Mackay matrix exactly have entries, really nice entries corresponding to Fibonacci numbers. And there's beautiful symmetry in these matrices. So under this fusion product, when you tensor the 1 with 1 an odd number of times, you get certain Fibonacci coefficients. And when you tensor with 1 even number of times, you also get Fibonacci numbers. So a comment, Chebyshev polynomials are everywhere dense. numerical analysis here too. And that's because the tensor rule basically forces you to. Questions. Suppose you take a finite dimensional Hopf algebra and you take a finite dimensional H module. When is it diagonalizable? When is the Mackay matrix diagonalizable? It's not true for the finite quantum group and its two-dimensional module. Okay, what's a good notion of the character table for a Hopf algebra? So there are a bunch of possibilities, but they all have assumptions, lots of assumptions on the Hopf algebra. Is the character table related to eigenvectors and Mackay matrices? Thank you.